We want to know what the inside of the sun looks like. That makes sense. The sun is our star. It powers everything on Earth. It's huge and bright, but we can't just cut it open or send a probe inside. It's too hot, it's too dense. So, how do we even begin to figure out what's going on in there? It's a tough problem. Imagine trying to understand a super complicated machine without ever seeing its internal parts. You can only watch it from the outside, you can see what it does, you can hear its sounds. Maybe you can feel its vibrations. From these clues, you have to piece together a picture of what's happening inside. That's a bit like what scientists do with the sun. They use clever ways to get hints and clues. They look for signals that come from the deep interior. They use physics to build models. And then they check if those models match the signals they observe. First, let's talk about why we can't just see inside the sun. The sun is not a solid object. It's not like the Earth, with a solid crust and a molten core. The sun is a giant ball of gas. And not just any gas, it's extremely hot gas. It's so hot that the atoms themselves are broken apart. We call this plasma. Imagine steam, but millions of times hotter and denser. Light can't just pass through this plasma. Think about a very thick fog here on Earth. You can't see through it. The light from a flashlight bounces off all the tiny water droplets. It gets scattered everywhere. The sun is like that, but much, much worse. The plasma inside the sun is incredibly dense. It's so dense that a photon, which is a particle of light, can only travel a tiny distance before it bumps into an electron or an ion. It gets absorbed, then re-emitted, then absorbed again, and re-emitted again. This happens over and over and over. It takes a really, really long time for light to get out of the sun's core. Scientists estimate it can take hundreds of thousands of years for a single photon to make its way from the center to the surface. It's like trying to walk through a stadium full of people, but every step you take, you bump into someone and have to change direction. You eventually get out, but it takes ages. So there is no direct window into the sun's interior. No telescope, no matter how powerful, can peer through that opaque plasma. It's a wall of superheated gas. But we do know some basic things just from looking at the sun from the outside and using fundamental physics. We know the sun is huge. It has an enormous amount of mass, and because it has so much mass, gravity is pulling it inwards with incredible force. If there wasn't something pushing back, the sun would just collapse in on itself. That something pushing back is the heat and pressure from nuclear reactions happening deep inside. It's a balance. Gravity pulls in, heat and pressure push out. This balance is called hydrostatic equilibrium. We also know how much energy the sun sends out. We can measure its brightness very precisely. And that amount of energy is massive. It's been shining for billions of years, and it's going to keep shining for billions more. If the sun was just burning wood or coal, it would have run out of fuel ages ago. Even chemical reactions can't explain that much energy over that much time. The only process we know that can produce that kind of energy is nuclear fusion. This means that atoms are combining to make heavier atoms, and in the process, they release a tiny bit of their mass as pure energy. Okay, that's the famous E make 2 equation at work, and we know what the sun is mostly made of. We can look at the light coming from the sun's surface and split it into a rainbow, a spectrum. The different elements leave different fingerprints in that spectrum. We see a lot of hydrogen and a lot of helium. This is perfect for nuclear fusion. Hydrogen atoms are the fuel. They combine to make helium. So just from these basic ideas, we can guess a general structure. There must be a very hot, very dense core where fusion happens. That's where all the energy is made. Then, that energy has to travel outwards. It probably travels in different ways in different layers. And finally, there's the surface we see and the thin atmosphere above it. This general picture is what scientists started with. But to get details like exact temperatures, densities, and how fast different layers rotate, we need more. One of the most powerful ways we see inside the sun is through something called helioseismology. It's a fancy word, but it just means sun earthquake study. It's like studying earthquakes on Earth. When an earthquake happens, it sends waves through the Earth. Scientists can measure those waves on the surface. Different types of waves travel at different speeds through different materials. A wave goes faster through dense, solid rock than through molten liquid. By analyzing how long it takes for waves to travel from one side of the Earth to another, and how they behave, we can figure out what the Earth's interior looks like. We know about the Earth's core and mantle because of seismology. The sun doesn't have earthquakes in the way Earth does. It's a ball of gas, but it vibrates, it rings like a giant bell. These vibrations are caused by the turbulent motion of gas in the outer layers of the sun. Imagine a pot of boiling water. The bubbles rise, break, and new bubbles form. This constant bubbling and churning creates sound waves. These sound waves then travel through the sun's interior, they bounce around, some go deep, some stay near the surface. They reflect off different layers and interfere with each other. We can't hear these sound waves directly, but we can see their effects on the sun's surface. When the sun vibrates, parts of its surface move up and down. These movements are tiny, just a few meters per second, but we can detect them using something called the Doppler effect. It's the same effect that makes a siren sound different when it's coming towards you compared to when it's moving away. Light from parts of the sun moving towards us gets a little bluer. Light from parts moving away gets a little redder. By precisely measuring these tiny shifts in color, we can map the up and down motions all over the sun's surface. These surface motions aren't random. They form patterns. They look like millions of little ripples on the surface. And just like those ripples, they tell us about the waves traveling inside. Different patterns of ripples correspond to different sound waves traveling through different depths of the sun. So, how does this help us understand the inside? The speed of sound in the sun's plasma depends on its temperature and its density. If a sound wave travels faster in one region than another, it means that region is hotter or denser. By precisely measuring the patterns and timings of these surface vibrations, scientists can work backwards. They use complex mathematical techniques to create a detailed map of the sound speed throughout the sun's interior. And from that sound speed map, they can figure out the temperature and density at different depths. For example, waves that penetrate deeper into the sun move much faster because the core is incredibly hot and dense. Waves that just skim the surface move slower. This lets us build a precise picture of the sun's temperature and density from the core right out to the surface. Helioseismology has taught us a lot. It confirmed that the sun has a distinct core, a radiative zone, and a convective zone. The core is where the highest sound speeds are, meaning it's the hottest and densest. It's where the fusion happens. Then there's the radiative zone. Here, energy is carried by photons bouncing around. Sound waves travel through this region. And then there's the convective zone. This is the outer third of the sun, where gas bubbles up and down, carrying heat like boiling water. Helioseismology clearly shows this boundary between the radiative and convective zones because the sound waves behave differently when they hit this transition point. Another amazing thing helioseismology told us is how the sun rotates. We know the sun rotates. But since it's a ball of gas, different parts can rotate at different speeds. From the surface, we see that the equator rotates faster than the poles. Helioseismology showed us that this differential rotation, where the equator spins faster, extends all the way through the convective zone. But once you get deeper into the radiative zone and the core, the sun rotates more like a solid body. This discovery was important for understanding how the sun's powerful magnetic field is generated. The churning, differentially rotating plasma in the convective zone acts like a giant dynamo, creating the magnetic field that causes sunspots and solar flares. So helioseismology is like taking the sun's pulse and listening to its internal rumblings. It gives us a very detailed picture of the physical conditions: temperature, density, pressure, and rotation at almost every depth within the sun. It's an incredible feat of measurement in mathematics, but there's another, even more direct way to study the sun's core: neutrinos. Neutrinos are tiny, tiny particles. They are one of the most mysterious particles in the universe. They have almost no mass. They have no electric charge. And the most important thing for our purposes, they hardly ever interact with other matter. They are often called ghost particles because they can pass right through everything, even through entire planets, without hitting anything. Why are neutrinos important for the sun? Because they are made in the sun's core. When hydrogen atoms fuse into helium in the core, along with photons, neutrinos are also produced. These neutrinos are born in the very heart of the sun, and because they interact so weakly with matter, they don't get stuck like photons do. They don't bounce around for hundreds of thousands of years. As soon as a neutrino is created in the core, it zips straight out of the sun almost at the speed of light. It takes just a few seconds for a neutrino to travel from the center of the sun to its surface, and then about 8 minutes to reach Earth. This means that neutrinos give us a real-time, direct look into the nuclear fusion processes happening in the sun's core. They are the only direct messenger we have from that super hot, super dense region. If we can detect them, we can confirm that nuclear fusion is indeed happening as we expect. We can also measure the rate of fusion, and the energy of the neutrinos tells us about the temperature of the core. Higher core temperatures produce more energetic neutrinos. Detecting neutrinos is incredibly difficult, precisely because they interact so rarely. They pass right through you, through the Earth, through everything. To catch them, scientists build massive detectors. These detectors are usually buried deep underground. This is to shield them from all other particles that constantly bombard the Earth from space, like cosmic rays. We want to catch only neutrinos from the sun, not a bunch of noisy background particles. These detectors often consist of huge tanks filled with super pure water or special liquids. When a rare neutrino does hit an atom in the water or liquid, it creates a tiny flash of light. This light is called Cherenkov radiation. It's like a sonic boom for light. Super sensitive detectors on the walls of the tank record these flashes. By studying the flashes, scientists can figure out the energy and direction of the incoming neutrino. When scientists first started detecting solar neutrinos in the 1960s, they ran into a problem. They detected far fewer neutrinos than their models of the sun predicted. This was a huge puzzle. It became known as the solar neutrino problem. There were two main possibilities: either our understanding of the sun's core was wrong, or our understanding of neutrinos was wrong. This was a really tense time in physics. Our model of the sun was pretty good, largely based on those foundational physics principles in early stellar models. But the neutrino results didn't match. For decades, scientists worked on this problem. Eventually, it turned out that our understanding of neutrinos was incomplete. We discovered that neutrinos aren't just one type. They come in three different flavors, and they can change from one flavor to another as they travel through space and matter. This process is called neutrino oscillation. The detectors on Earth were only designed to catch one specific flavor of neutrino. So, if the neutrinos produced in the sun's core were changing flavors on their way to Earth, it would explain why we were only seeing a fraction of them. Once scientists accounted for neutrino oscillation, the number of detected neutrinos perfectly matched the predictions from our solar models. This was a triumph for both solar physics and particle physics. It confirmed, with direct evidence, that nuclear fusion is happening in the sun's core exactly as we thought. It also confirmed the core's temperature, and it led to a Nobel Prize for the discovery of neutrino oscillation, a huge new piece of the puzzle of fundamental particles. So, neutrinos really are our direct window into the sun's power plant. Finally, the third big way we understand the sun's interior is through computer models and simulations. This might sound less direct than neutrinos or helioseismology, but it's absolutely crucial for tying everything together and for helping us understand why the sun is structured the way it is. Scientists use all the known laws of physics to build virtual suns on powerful computers. These laws include gravity, which pulls everything together. They include thermodynamics, which describes how heat moves and how gas behaves when it's super hot and dense. They include nuclear physics, which tells us how hydrogen fuses into helium and how much energy is released. They also include fluid dynamics, which describes how liquids and gases move, especially in a turbulent way like in the sun's convective zone. A computer model starts with a giant ball of mostly hydrogen and helium. It then applies these laws of physics. So gravity pulls it in. The pressure from the gas pushes out. As it compresses, it heats up. Eventually, in the very center, it gets hot and dense enough for nuclear fusion to start. The model then calculates how the energy produced in the core moves outwards, layer by layer. It calculates the temperature, pressure, and density at every single point inside the virtual sun. It can even calculate how the sun changes over billions of years. These models are incredibly complex. They solve equations that describe how mass is conserved, how energy is transported, how pressure balances gravity, and how energy is generated. They are constantly refined. The real power of these computer models comes when we compare their predictions with the actual observations from helioseismology and neutrino astronomy. If the model says the core should be 15 million degrees Celsius and the neutrinos in helioseismology agree, then we're pretty confident in that part of the model. If the model predicts a certain rotation rate for the convective zone and helioseismology confirms it, then the model is good. But if there is a disagreement, that's where the real science happens. For example, if the model predicts more energetic neutrinos than we observe, or if helioseismology shows a different temperature profile than the model, then scientists go back to the model. They check their assumptions. Maybe the known properties of plasma at extreme temperatures need to be updated. Maybe there's a physical process they haven't included or understood correctly. Maybe the amount of a certain element in the sun was a bit off in their initial input. It's a continuous process of comparing, refining, and improving. This iterative process where theory of the models is constantly tested against observation, helioseismology, neutrinos, is what makes our understanding of the sun so robust. When all these different lines of evidence, independent ways of looking at the sun converge and tell us the same story, we become very confident in that story. So, what does this combination of clever physics, direct signals, and powerful computers tell us about the inside of the sun? At the very center is the core. This is the hottest and densest part. It's about 15 million degrees Celsius, about 27 million degrees Fahrenheit. The pressure here is astronomical, billions of times greater than Earth's atmospheric pressure. The core extends out to about a quarter of the sun's total radius. This is where hydrogen atoms fuse to form helium. It's the sun's engine room, producing almost all of its energy. The density here is incredible, about 150 times the density of water, which is about 8 times denser than solid gold. Even at these extreme conditions, the material is still a plasma, not a liquid or solid, because of the immense temperature. Surrounding the core is the radiative zone. This zone extends from the edge of the core out to about 70% of the way to the sun's surface. In this region, the temperature drops from about 7 million degrees Celsius, 13 million degrees Fahrenheit, at its inner edge to about 2 million degrees Celsius, 3.5 million degrees Fahrenheit at its outer edge. The density also decreases significantly. Here, the energy generated in the core is transported outwards primarily by photons. These photons don't travel in a straight line. They are constantly absorbed and re-emitted by the dense plasma. It's a slow, random walk that takes hundreds of thousands of years for energy to pass through this zone. It's like being in a super crowded room where you keep bumping into people and changing direction. Beyond the radiative zone is the convective zone. This is the outermost layer of the sun's interior, extending from about 70% of the way out to nearly the surface. Here, the temperature and density have dropped enough that the plasma becomes opaque to radiation. This means that photons can no longer efficiently carry the energy outwards. Instead, the energy is transported by the physical movement of the gas itself. Think of a pot of boiling water. Hot water from the bottom rises to the top, cools, and then sinks back down. This creates convection currents. In the sun's convective zone, huge bubbles of hot plasma rise towards the surface, carrying energy with them. As they reach the surface, they cool down and then sink back inwards to pick up more heat and start the process again. These rising and falling columns of gas are what create the granular pattern we can see on the sun's surface. This constant churning motion in the convective zone is also crucial for generating the sun's magnetic field. Finally, we have the visible photosphere, which isn't truly the inside, but is the layer we see. It's technically part of the sun's atmosphere. This is the thin layer where the plasma becomes transparent enough for photons to finally escape into space. The temperature here is much cooler, around 5,500 degrees Celsius, 10,000 degrees Fahrenheit. This is the surface we observe when we look at the sun. Above the photosphere are the sun's outer atmosphere layers, the chromosphere and the corona, which are even hotter but much less dense. So, when we talk about knowing what the inside of the sun looks like, it's not about physically seeing it. It's about a fantastic detective story. It's about using the vibrations on its surface to map its internal structure. It's about catching elusive particles that fly directly from its heart. And it's about building detailed computer models based on the laws of physics, then rigorously testing those models against every piece of evidence we can gather. It's a testament to human ingenuity. We can't touch the sun, we can't go there. But through careful observation, brilliant theoretical work, and a lot of patience, we have pieced together a remarkably clear and detailed picture of its hidden depths. And that picture tells us that the sun is a dynamic, complex, and incredibly powerful star, whose inner workings we now understand better than ever before. It's an ongoing process, of course. Scientists are always looking for new ways to refine our understanding, always asking new questions, and always pushing the boundaries of what we can know about our universe, even without directly seeing it.